Here's our third video from section 7.3, and we've kind of already talked a little bit about domain and range from a previous section, but let's talk about it one more time, and let's determine the domain of different types of functions, whether they're linear or nonlinear. So remember, an equation of a line, a linear function, looks like y equals mx plus b, or f of x equals mx plus b. We know that a line is a straight line. It has a slope. It could go positive. The slope could be negative. We could have even a horizontal line, right? And so all x values are defined on any sort of line, maybe not a vertical line, but on other lines besides the vertical line. And so we can say that our domain is all real numbers. My line's going to go to the left, my line's going to go to the right, and it's going to include all x values. So my domain would be negative infinity to infinity. Do you remember an absolute value function? If I have an absolute value function, remember the absolute value function kind of looks like a V shape, maybe an upside down V or a V shaped. And so I know that that V is going to go to the left, it's going to go to the right, it's going to include all x values in that function or graph. And so we can say that our domain for any absolute value function is also all real numbers, negative infinity to infinity. All right, what about polynomial functions? This one happens to be a cubic function. I have an x cubed plus 5x minus 2. Well, any polynomial function, remember, kind of has squiggly lines. Sometimes there's more squigglies than others, depending on how many terms and what your coefficient is. But it's going to continue to go to the left. It's going to continue to go to the right. We don't have any denominators to worry about, any holes to worry about. So it looks like my domain then on any polynomial function is also negative infinity to infinity. Same idea with quadratics. Do you remember a quadratic function has that x squared in it? We know that a quadratic graph is going to be a parabola or a U-shaped graph, maybe an upside down U possibly. And so it's going to go to the left, it's going to go to the right. It's not going to have any issue with or restrictions in my domain. So my domain for any quadratic function is also all real numbers. So far all of these functions have domains that include all x values. All right, but there is a function that we have to worry about having domain restrictions. Remember those rational functions? Anytime I have a polynomial in the top, in my numerator, and a polynomial including a variable in the denominator, we've got to worry about that denominator equaling 0, right? So I've got to figure out what's going to cause that denominator to be 0, and that's going to be a restriction in our domain. So if I set that denominator equal to 0, I know that x can be anything except for x equals 2. That's going to cause that denominator to equal 0. So I can say in this rational function that my domain is negative infinity to 2, and then again from 2 to infinity, but making sure we don't include 2. That's the only x value that won't work in our domain because it's going to cause that denominator to equal 0. So make sure you're looking out for that anytime you have a rational function. Okay, so can I give you then a whole bunch of different functions without graphs, and can you determine what their domain is? Okay, so let's first start by stating whether each equation describes a linear function, an absolute value function, a polynomial function, a quadratic, or a rational function. And then let's determine the domain. All right, look at A. G of x equals x over x plus 1. Well, I don't know about you, but I just saw a red flag, right? As soon as I see that denominator, I know that I have a rational function, and that denominator cannot ever equal 0. So because this is a rational function, we've got to figure out what domain restrictions we have. Let's set that denominator equal to 0 and solve, and it looks like my domain is everything except for x cannot equal negative 1, right? So can I say my domain is negative infinity to negative 1? And then again from negative 1 to infinity, making sure I use parentheses so I know I'm not including negative 1. But all other x values should work. All right, what about B? H of x is equal to the absolute value of x minus 7. Well, that's obviously an absolute value graph. And do you remember our absolute value graphs kind of have a V shape? It's going to go to the left, it's going to go to the right. We don't have to worry about any denominators here. So it looks like my domain would be all real numbers or negative infinity to infinity on any absolute value function. All right, what about these next two? C says we have a function f of n equals 15 minus 10n. That looks a little bit different because they're using different variables on us instead of always just using x's and y's. And that's okay. It means the same thing. If you're more comfortable, what if you write it in a different order? Maybe f of n equals negative 10n plus 15, putting the negative 10n first and the positive 15 last. And if you're even more comfortable, instead of calling them n's, call them x's and y's, right? They mean the same thing. You've got an input, you've got an output, x's, y's, n's, f of n's, they mean the same thing. But as soon as I do that, maybe that kind of looks a little more familiar to you. And to me, this looks like a linear equation, right? It has a slope of negative 10 and a y-intercept of 15, and it would look something like that. It's going to go to the left, it's going to go to the right. There's not going to be any domain restrictions. There's no denominator there. So it looks like my domain here is all real numbers because of that linear function. All right, what about D? It says g of t is equal to t squared plus 4t minus 5 over 6. Ooh, and there's a denominator. But look at this denominator. This denominator doesn't have a variable in it. It's never going to change. It is always going to be a 6. So this is not actually a rational function like maybe you thought it was just because it was a fraction. Because that denominator is a number, a constant, what I could actually do is rewrite this into 3 smaller fractions with their own denominator of 6 instead of one big fat fraction with a common denominator. So I can really write this as 1t squared over 6 plus 4t squared over 6 minus 5 over 6, right? 3 separate fractions instead of one big fraction. And then you notice that yes, these are fractions with denominators, but really that denominator is never going to change. Really, we just have fraction coefficients. And so my only variable here is the t squared and the t. And so if I have a t squared as my variable, an x squared as my variable, isn't that really a quadratic function? It just happens to have a coefficient that's a fraction instead of a whole number. But it's not going to change its shape. It's still going to be a quadratic. It's still going to be one of those U-shaped parabolas. It's going to go to the left. It's going to go to the right. There are no domain restrictions. I should be able to plug in any t and get out any value. There's no denominator that's going to change and ever be 0. And so my domain should be all real numbers or negative infinity to infinity. It looked a little bit funky at first, but just be careful. Because there's no variable in that denominator, we don't have to worry about domain restrictions on that one.